Okay, this is the analyzing data tutorial. We analyze data in the context of lab. So just for a little background on the role of lab and experimentation in physics class, you can make some comparisons to an English, what would you call, essay, maybe a history research paper. And of course scientific experiment. And it's not a perfect fit or comparison, but I think it's helpful still. So for an English essay, maybe have thesis, body, history, you have a thesis, you have a body, you have conclusion. Alright, the thesis is what you want to prove. In both cases, the body provides evidence and explanation. Of evidence. Provides evidence and explanation of evidence. Okay, and besides explanation, argument is a part of it. Alright, that explanation is given to argue your point. And then I'll just call the conclusion the wrap up. I won't go into detail about what it is. So in a scientific experiment, you have a hypothesis or a scientific question you want to answer. Okay, and then, well, here's where it diverges a little bit. Instead of going out and researching, and then like you would say for a history research paper, research thesis, but you only take the results of your research and the results go in the body. So research thesis and use results. Okay, well, we have one difference here in that part of the lab is showing your research being your experiment. So we actually do, as part of our, let's just call it a body for the sake of paralleling these three, we have extra stuff, meaning materials, procedures, variables, defining variables. Alright, we do not have data right away, so we have to do an experiment to get data. And then after that, alright, well, once data isn't obtained, then it looks a lot like this. Use your results to explain your thesis. So, but how you use your results are different, and that's what this tutorial gets into. Just like a conclusion there, there's also a conclusion here, but again, we're not talking about that. It's not as important. Once data is obtained, okay. Once data is obtained, analyze it. Research, thesis, use results. Analyze it and use it to prove/disprove hypothesis. All right, so that completes the process. So the main difference is this whole boxed research category is not present here. It's empty. All right, you don't have to show it if you do any research for essays. Yeah, you do book research for essays. You don't have a documentation of that process in either of these. So the real main thing you're adding is this documented process of finding your data. And then, of course, the nature of the data you collect is numerical, which is generally different than both of these. But even though it's numerical, you do the same processes, general processes. You use that data to support, to make up, construct arguments to support or refute your hypothesis. So let me go over the process, since the actual process of analyzing data is different than the actual process of, doing research for an essay or history, or not doing research, I'm sorry, is different than the process of, using your history and English research to prove or disprove your thesis. Let's go over the process of analyzing data. Okay, so first of all, analyzing data. You need data. You need data to analyze. So you shouldn't be thinking about analyzing data until you have something there. And just having the data on your paper does not mean you've analyzed it. It's just data. To analyze the data is to make meaning. So I'm going to write that in here. To analyze the data is to use the data to create new understandings of natural phenomena. And I will simplify that as it creates meaning. So how do we create meaning from a bunch of data points? Well, how do I erase the board? I'm sorry. I'm running into some technical problems. Here we go. Okay. So, the process. Let's get down to the process. You've seen it before on your quizzes, but step one, let's use a different color now. Is this better? No, that's not better. This probably isn't better either. Oh well. Well, not oh well. I'll change it. Step one. The first thing I would do is represent your data visually so it is easier to use the data. Well, it's easier to recognize patterns and use the data to create new meaning. And use the data to create meaning. All right, and how do we do that? One big word. A visual representation is a graph. All right. And what do you graph? Well, you graph your experiment's variables. Your experiments independent and dependent variables. So once you make a graph, I mean, all you've done was you've put points on a paper. You know, you haven't really made them meaningful yet. You've just made a representation that we can then use to analyze the relationship, any possible cause and effect relationship between the variables. So if this is an x versus t graph, and we have a line, or if this is not a line, we're not there yet, and we have a bunch of points. All right, or it's an x versus t graph, and our points look like this. All right, they're just points right now, but we can create meaning by making a best fit line. I'm not going to call this number 2 yet. No, it's like 1.5. We'll call it 2 still. All right. We have to make meaning by recognizing patterns. So there's 2 different patterns to recognize on 2 different graphs. The pattern here is a linear pattern, so I made a best fit line. And the important part of that is that that line represents the trend of the data. Some of the data points are not on the line, but there is somewhat of a balance between how many points are not on the line and above it, and how many points are not on the line and below it. The more balance it has in that respect, the better it is. This other one does not have a straight line relationship. It has, and that's not even a good line. All right, this relationship we see is curved. All right, so we see a steadily increase. So by making these trend lines, is the first step to making your graph, no, I'm going to say your data, making your collected data have meaning. The fact that x and t change, the fact that x changes as t changes, means there's some kind of, you're showing a causal relationship between time and where it's at. So by showing this relationship, you're creating meaning. Now, this is just a physical representation, pictorial representation, but what does it mean in the context of your experiment and the things you were testing? Well, we have to interpret. So continuing along this line, interpreting your graphs, or interpreting your lines and curves. All right, so to interpret your lines and curves, I'm not going to go super in depth on this, but I will remind you that for a best fit line, find the slope. All right, the slope is the rise over the run. So I'm going to pick 2 points on my line, and I'm going to find out how much the x changes, and I'm going to find out how much the t changes between those points. And then that will tell me the slope of the line, and that will tell me actually the relationship between the x and the t. That says as the x increases, the t will increase by a proportional amount in this particular x versus t graph with a linear trend line. All right, so that's all you really have to do for if it's a line. If it's a curve, well, you have to do more sophisticated math on it, but since we're only really working with algebraic type stuff and not really anything more complicated, we have to do a kind of a process. And this process is we're actually going into the graph and doing dirty work. So I'm picking equally spaced time periods. So I can arbitrarily call that 1 second, 2 second, 3 second, 4 second. It's not actually probably representative, but the important part is not the numbers, it's that they're equally spaced intervals. And then during those equally spaced intervals, I am finding out how much the graph goes up. So I see that if I do a line across for the time, whatever's left in the purple is how much it increased from one time period to the next. So we have an increase of this much here, of this much here, and of this much here. And if you see, the green line gets longer, the green lines get longer. So the rate of increase of x is going up as time passes. Literally, I just stated what's happening. And if I'm interpreting this, then I can say that this is increasing velocity or acceleration. All right, so this is the analysis part of step 2. So this is like the very meaty technical part. This is where you are really taking the meaning from the data you collected and making it and connecting your data to the real world, to maybe the physics concepts that we've been learning. And the last step is basically use data from, I'm not going to say from, I'm going to say use data extracted from part 2. Any data you got from that. Maybe it's the slope. Maybe it's that, maybe you read the graph in specific places and saw that, it increased 2 meters the first second, and it increased 4 meters the second second, and it increased 6 meters the third second. Any kind of data extracted from part 2 in order to make as strong of a case possible that your hypothesis was true, false. Let me write that out. Was true, false, or inconclusive. And the good thing is that, unlike history and literature essays, is that you don't have to prove your hypothesis true. That's not a requirement for doing a good experiment. You have to prove, nature kind of does what it does, and just because we want nature to work a certain way doesn't mean it always will. So the good news is that we've succeeded whether or not our hypothesis is true or false. And if it's inconclusive, then we haven't failed either, because we can learn from this. We can take from this experience maybe certain things we can change or modify about this experiment that will make, maybe if and when we do it again, it might make the difference and allow us to get a true or false hypothesis out of it. So inconclusive, it just means you're not done with your inquiry. True or false, that would mean, I guess that could mean you're done. False, maybe try a different direction. True, you verified what you're trying to verify, and I guess you move on to something else. I haven't thought that part through very much, but inconclusive is definitely the judges are still, the certainty is not there yet, so there's more work to do. Definitely an inconclusive. If you have an inconclusive hypothesis, you don't have certainty yet, and you have to do more testing. So practice. How do you practice this? Well, I give you data tables, and you do the analyzing process. So XT, and you do the whole thing. So I'll say 1. This data was collected from a tumble buggy. So at 100 centimeters, I should make that readable. X centimeters, T seconds. At 100 centimeters, let's say it took 0.1 seconds. 205 centimeters, it took 0.2 seconds. I'll say 0.21 seconds. At 303 centimeters, it took 0.29 seconds. And at 400 centimeters, it took 0.40 seconds. All right, so that is your data. Analyze data. So instead of analyze data, do an analysis. Step 1, step 2, do an analysis. Step 1, 2, 3, and in order to prove the hypothesis, as the position of the tumble buggy increases, the time increases by the same factor or the same proportion. Basically, what I'm saying is they're proportional. All right, so that is the hypothesis that you have to prove or disprove. And let's see if the data does it. And you have one more, which represents the second lab you did. So this data was collected from a ball rolling down a ramp. All right, and here's your data. All right, x meters, t seconds. And so let's say it's 0.2 seconds, 0.4 seconds, 0.6 seconds, 0.8 seconds. All right, and your distance, 1 meter, 2 meters, 4 meters, 8 meters. I'm making this nice. All right, so for this, of course, you do an analysis. Step 1, step 2, step 3. And your hypothesis make it exactly like the other one. In order to prove the hypothesis, as the time on the ramp increases, the rate of position change increases. Okay, basically this is saying that every second of time or every period of time that it's on the ramp, more and more distance is going to basically be traveled than in each of the previous seconds. So basically it's speeding up. It's got an acceleration. So those are your two problems. Good luck.